Merhaba.
Merhabalar hocam.
Merhaba. Latif sen misin?
Evet, Hatice.
Ben bir şehir olabilir, bu oturumun bir e, hostu olabilirsem evet. Şimdi
Sanki öyle gözüküyorsunuz hocam. Session chair
şimdi
aynı
ama
zamanda.
mesela screen share'lerde hiç hakkım yok.
Hmm.
Yani şu anda e, o hakkı vermeyeceklerdi bana. Şöyle bir yoklama yapalım. Bunların İngilizce olması şartı yok herhalde.
Hı hı.
Latif 49'u sunacak. 87 nolu paper'ın sunucusu var mı?
Yasin
Buradayım.
Yılmaz.
Yasin.
Yasin burada. 109 Multi-layer Perceptron Hardware Accelerator on the RISC-V prosesör diye Nazım, Berkay, Yusuf. Sanırım İlayda burada.
Aynen.
Tamam.
Buradayım hocam.
Bir kişimiz eksik. 109 nolu paper. Onu bir soralım. Tamam. Dakikamız var.
Hocam bu arada söylemeden edemeyeceğim. Sakal inanılmaz yakışmış.
Bunlar kayda alındı biliyorsun değil mi?
Tamam hocam.
Evet, bakalım şimdi. Latif herhalde Erzurum'da. Değil mi? Latif neredesin?
Bayburt'tayım hocam.
Bayburt'tasın. İlayda Ankara'da. Yasin sen neredesin?
Hocam Elif Ankara'da.
Elif Ankara'da, İlayda. Doğru, pardon ya. 22 İlayda. Sen İstanbul'dasın. Yoksa
Yok,
Almanya'da mısın?
Almanya'dayım hocam.
Gittin demek.
Evet.
Bunu ben yapmadım.
I am Bursa.
Hemen bir şey mi?
I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa, I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradia Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Jumalıkızık, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suruçtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jantik from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegern köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagas and hajavat. I am handicrafts at Erganda Bridge, a steel knife forged in fire, a smooth silk shawl from Kocahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Okay. Yeah, it seems to be all this nice present after the nice video and nice food. We are ready to present ready to start the session. So we have today 4 talks, and I believe 3 of them is here. And please, the third presentation, if someone come, Nazim, Berkay, Yusuf, or Berna, please let me know from the chat, okay? So now it's time for the first presentation. And for each presentation, we have 15 minutes. And please keep your time, and also at least leave 5 minutes left for the question session. And okay, first talk, I give the word to Latif. Latif, you can share your presentation and we can start. Can you share it?
I'm trying.
Okay, you did it.
Please inform me if you see my screen.
I see, and also I expect that the others attendees can see. Okay, you can start.
Okay. I think I'm ready. First of all, I want to thank all Alaco team for this great organization. And also I want to thank Professor Mustak for his this introduction, and it's a really honor for me to present this under his chair. Hello everyone, again, I am Latif. Today I will be presenting custom TTA operations for Kyber algorithm. So let's check out first the content. First of all, I will try to give you the information about the background of the subject of the topic. What's post-quantum cryptography, what's NIST post-quantum cryptography standardization process, and why we need this kind of thing. And then I will introduce the transport trigger architecture, which is, let's say, NIRBI architecture, NIRBI processor architecture. And it's very interesting. I am sure you will notice it. And then I will try to tell our contributions to this topic. I mean, both post-quantum cryptography and also the transport trigger architecture. Then finally, I will share our obtained results. And then at the end, we can make a question and answer session. So let's start with the post-quantum cryptography. What is it? But first, we need to know about quantum computers, but it's just simply. I'm sure you all heard about quantum computer development projects. Actually, in the past, when someone talks about quantum computers, it was just a dream, and no one believes that we will have practically used quantum computers in the past. But in recent years, especially in the last 10 years, there has been many big projects. These projects are supported actually by states, by big states, by developed states. And as you know, Google, IBM, or Lockheed Martin, and any other huge companies progressing these projects. I'm sure many of you heard about their interesting results. They announced that they achieved the quantum supremacy, for example, Google, and you see, by the way, in this picture, the Google's Sycamore processor core. This is called a quantum computer, and it's, as far as I know, 54-bit quantum processor by Google. On the other hand, China claims that they have the faster, even the fastest quantum computer ever built, and also Japan, United Kingdom, and any other countries progressing these high-budget programs to develop a practically used quantum computer. So we can say that we will have a practically used quantum computer in this decade. Many scientists, many experts believes that even if there are still major hardnesses of production techniques, many scientists believe that we will achieve to produce such computers. But why we do that? I mean, why we need these quantum computers? Because quantum computers have accelerated some problems, not all, but some problems very faster than any other classical supercomputers. These kind of problems, we can say optimization and search problems, big data analysis. This is very important for machine learning techniques, and anything else, chemical and biological research, especially the DNA research, is very important for quantum computers. I mean, quantum computer is very important, this kind of research. And also we will have chance to make huge simulations about climate change or space studies. And there's a tricky thing. We can also be also used the quantum computers for cryptanalysis. So what is it? Simply, the cryptanalysis is the effort of breaking algorithm, a cryptography algorithm. So why this is important? In 1994, the famous American mathematician Peter Shor published a work about a quantum computer algorithm, a polynomial time quantum computer algorithm, and he showed that a quantum computer can solve integer factorization problem. What is integer factorization? Please imagine that you have a given number n and you try to find its prime factors. This is simply called integer factorization problem. This is a very important problem, and its variance is also so important because widely used public key cryptography algorithms such as RSA, elliptic curve cryptography, or digital signature algorithms used today. These are all based on this integer factorization problem. The hardness of the integer factorization problem provides the security. But Peter Shor showed that this problem can be solved very faster with a sufficient quantum computer. So this is actually shocking, because if someone has a quantum computer, then he or she can solve this problem, and of course at the end he can break your cryptography system, and he can easily obtain your information or a state's information. I mean, it's very threatening. So cryptographer has to find new kind of cryptography, new kind of public key cryptography algorithms. And this had to be resistant both quantum computer and classical computer attacks, because, you know, we will be still using classical computers, but maybe some of the states or some of huge companies will be used quantum computers. So the new public key cryptography algorithms in quantum age, let's say, have to be resistant both quantum computer and classical computer attacks. Cryptographer has to find new techniques, I mean, and these new techniques had to be based on some other hard problems that quantum computer cannot solve effectively. Maybe you can think that it's not urgent because no one has a quantum computer as far as we know for now. And let's think about it 10 years later, but it's not like this, because your information or a state's private information can be saved now. And maybe 10 years later, a spatial service can solve this problem, this information with a sufficient quantum computer. So I want to state that this is a need for now, not for the future. And we urgently need these kind of cryptography techniques, and we use these techniques almost everywhere where we use cryptography. Also, we have to create designs for these kind of techniques, both in hardware and both in software. And also, this is very important, we have to set standards like in RSA or elliptic curve cryptography or advanced encryption algorithm. We have to set standards because we want to use these crypto systems all over the world. So institutions or people needs to communicate each other with predetermined standards. So, and then we have to prepare application-specific hardware and software for this new architectures for these new algorithms. And as Mustak says, winter is coming, so we must be ready for this. And what we did until now. NIST, as you know, is a national institution in United States, has started a solution initiative in 2016. And they call this process as post-quantum cryptography standardization process. And the goal was develop, evaluate, and standardize proper algorithms for quantum age. But it's not a contest to determine, to pick a winner. But instead, this is a process to find secure alternatives, secure and effective alternatives, because as I said, we want to use these algorithms both in embedded systems and let's say large servers. So this process was started in 2016, and let's check out the timeline, what we did until now. In 2017, the first round algorithms are announced. And by the way, this process is an international and open process for all researchers. And during the round, during the first round, 69 submissions are accepted. And in 2019, the second round candidates announced, and as you see, many of the first round algorithms are eliminated during this process. And the third round was in 2020, and they announced that we have just 7 finalists, and these are the last, I mean, final round for the progress, and we will have standards, draft standards available by 2022. So let's check out what we have now. Actually, there are mathematical approaches for post-quantum cryptography, as you see here, but I don't want to give in detail. But we know we have 5 different approaches to the post-quantum to the mathematical base, let's say, for post-quantum cryptography. But if you check out the list here, you can easily deduce that the lattice-based methods are the prominent of the standardization process. The lattice-based cryptography methods are nearly all finalists uses these methods, but except 2 algorithms. One is McAlice and one is Rainbow. McAlice is a code-based cryptography, while the Rainbow is a multivariate cryptography. But the other ones is the other ones are using lattice-based cryptography methods. So I want to simply explain what is a lattice in mathematics. A lattice simply is a set of integer combinations of linearly independent base vectors. But please notice that these vectors are linearly independent, and we construct a set with these base vectors by just multiplying with integer numbers. And then we create 3D or multidimensional space grids, as you see from these pictures. You see here a 3-dimensional lattice at the left, and you see a 2-dimensional simple lattice in the left. So this is the definition of a lattice in mathematics. And how we will use this in cryptography for post-quantum cryptography, we can say that there are some hard problems. There are some NP hard problems defined in lattices, and these problems are not known to be breakable for quantum computer or classical computer attacks. Actually, there are many hard problems. There are many hard variants of these problems, but I just want to give simple examples. The famous one is the shortest vector problem. This is, by the way, used by the Andrew. Please remind that this is the entry is the one of the finalists of the standardization process. Andrew uses this shortest vector problem. This shortest vector problem is defined. Please have a look at the left side of the page. You see we are in a simple lattice, and we are given this lattice with B1 and B2 base vectors. And we have to find, the problem says us to find the shortest vector, but this is not the base vector. This is not one of the base vectors. And the problem says us to find the shortest vector in this lattice. This is one of the hard problems defined in lattices. And the other problem, the other hard problem is the closest vector problem. In this type, we want to, we are given again a lattice with B1 and B2 base vectors, for example, and we are given also an external vector. You see here, it's called CV. And the problem says us to find the closest lattice point to this external vector. This is called the closest vector problem. And the other famous problem is the learning with errors. It's called as learning with errors. And this problem is used by Kyber, Cyber. Please remind that these are also the finalists of the NIST standardization process. And you see at the right a simple explanation for this problem. Actually, this problem is based on the closest vector problem. But how we use in cryptography, I just make a simple example here. Suggest you are given this equation, but accept with this small error vector. And if you know B and A, then you can find secret S here. You can easily find this. You can easily compute this. But if I add a small error vector here, it's a bit tricky. This is called the learning with error problem with this small error adding. As I said, Kyber and Saber and many other algorithms, many other cryptography algorithms uses this phenomena. And have a look at what is Kyber algorithm. Kyber is one of the famous NIST standardization process finalists. And its security is based on this LV problem, I mean the learning with error problem, but it's using a variant, as I said, there are many variants of these problems. It uses model LV problem. The model mean here is that this algorithm determines a modulo for the integer numbers to make the calculation easier. And together with dilithium, please remind that this dilithium was the other finalist of the process, but dilithium is digital signature algorithm. Actually, of course, it's also a public key cryptography algorithm, and Kyber and dilithium forms the crystals family. They call this family as crystals. And they are using the same problem. They are submitted by the same researchers. Kyber is very famous because it's very easy to apply in both software and hardware. And also it's, let's say, fast calculated methods. So it's important, and personally, I believe that the Kyber will be the widely used post-quantum cryptography algorithm. In Kyber, lattice dimensions specified by the parameter key, and in submission package, when we check out it, we see three different parameter sets for three different NIST security level. As you know, NIST specified security level from 1 to 5. 5 is the highest security. And Kyber researchers offer, as I said, three parameter sets for level 1, level 2, and level 5. And shortly, let's check out how Kyber generate keys and encrypt and decrypt the information. First, please look at the bottom right of the page. First of all, a random key by key matrix are generated for key generation, and then we compute T, as you see here, with our secret key S. The secret key here is a vector, and we multiply it with a randomly generated matrix A, and we add a small error vector. And by this way, we specify our secret key as S and our public key T and I, and we publish this T and I to everyone who wants to connect us. And let's think someone wants to send us a message. So what he is going to do is he will compute these U and V vectors. As you see, he or she uses our public key and multiplying it with his or her private key and adding again a small error. By the way, these small error vectors has to be generated in same process. I mean, this E1 and E2 has to be generated, for example, in a binomial distribution process. And by this way, he generates U and V vectors, and ciphertexts are formed as U and V. And then when we want to decrypt the message, please notice that this message vector is
Latif,
complete.
you have already 24 minutes, also 25 minutes. So please
sorry.
your time. So this is
okay. I'm so sorry. Okay. Let me give short information about transport trigger architecture. Transport trigger architecture is a belief-like architecture, and you see here it's a structural example. It's a processor architecture actually, and as you see, we have transport buses and we have distinct functional units here. This is a NIV processor architecture, and it's very flexible, scalable, and customizable. And so we wanted to implement post-quantum cryptography processor by using this architecture. But how we gonna do this? Hopefully there are there is a design environment called co-design environment, and it's developed in Tampere University. Actually, it's simple because you just use script-based design, and using this tool you can easily create your own processor, and by this environment you can compile your code with retargetable compiler. Retargetable is very important, so I want to say about it. Retargetable means that the compiler adapts your machine automatically. This is very important when you compare it with RISC or complex instruction processors, and then you can generate your processor. Our first contribution was to provide 64-bit support to TC, because when we meet the TC, it doesn't have any support for 64-bit data, and we provide it. We are so just, let's say, happy to contribute such an important thing. And of course, we shared it with the TC team because it's an open source and free tool set. And then we started to design a processor for accelerating the Kyber algorithm, for designing an application specific processor. You see here our first designed processor, we call it TTA 64B, and it just uses 28 different operations and a fully connected bus architecture. You see here we used 4 transport buses, and each are connected as a fully connected bus. And we also designed TTA 64B2. It just uses 2 transport buses instead of 4. And then we started to design our custom operations for Kyber, and we implement it in VHDL. And then we integrate these custom operations to hardware databases and other parts of the tool to provide automatically generation of the desired processor. You see here we used profiling techniques in official C codes of Kyber, and we determined these operations. And then we created our custom application specific processor. As you see here, we designed 13 custom operations, and we integrated to this machine. And again, we defined a new processor, TTA 64C2. It just uses, again, 2 transport buses. By the way, you can determine the bus counts or the functional units you see here. And then I will shortly give the results. First of all, we checked out the performance results, and as you see, we can make these calculations 4 times or 5 times faster than 64-bit RISC-V cores, and we consume up to 4 times less energy according when comparing to the popular RISC-V cores. And let's check out the physical core characteristics. As you see, these cores have close chip requirements with the RISC-V cores, but to be fair, when doing this comparison, we exclude caches or floating point units from the RISC-V designs, to be fair. And we see that this kind of processor can be used in embedded systems very effectively because they are faster and they consume less power. But it has some disadvantages. We can say they need very long instruction words, and they have, for now, a lack of IP cores and software support. I'm so sorry for taking your time. Thanks for listening. If you have questions, I can answer it.
Latif, let's the question, please send the question to directly by email, because the talk was too extended. So it's better to start the next talk, okay? So they can send you the question personally by email, okay? Thank you for your presentation.
Thank you. So sorry about the latency.
No problem. Please try to keep it in 15 minutes. Try to your best, okay? Now we have time for the next talk. And next talk is titled Design and Implementation of 32 bits RISC-V Core. and it will present by Yasin Yilmaz, I guess. Yasin, are you here?
Yes, I am here. Can you hear me?
Okay, please put your presentation on the.
Okay, can you give me 1 minute? I have a few seconds. I will come back.
Meanwhile, we might have a question if you have any question. To Latif, of course.
Yeah, of course, I want to answer it if you have.
Okay, I am ready.
Okay, please start.
Can you see the presentation?
Yes, we can see it clearly.
Okay. Okay, hello again, Professor Yalcin, everyone. I am Yasin Yilmaz, fourth grade student from Istanbul Technical University, Electronics and Communication Engineering Department. I will present our work with the name Design and Implementation of a 32-bit RISC-V core. Let's get started. My presentation agenda will be as given here. First, I will briefly do an introduction on RISC-V and our purpose with this work. And then I will start describing our design process in 3 steps. And finally, I will conclude by summing up our achievement with the project and possible future work. Okay, let's start with the introduction. Okay, the RISC-V stands for Reduced Instruction Set Computer. It is an instruction set architecture that is a product of a 5-year project carried out in the University of California, Berkeley. The RISC-V ISA specifies the minimum set of instructions that a possible implementation should be able to fulfill, and additional subsets of instructions and higher level specifications for more complex designs. It's a very popular ISA that are used in many areas in both academia and industry, and it has its own RISC-V organization. RISC-V is open source, meaning it is accessible to anyone and free to use. As stated in the RISC-V organization website, the worldwide interest in the RISC-V is not because it's a great new chip technology. The interest is because it's a common, free, and open standard to which software can be ported, and which allows anyone to freely develop their own hardware to run the software. After that, our objective with our work was to produce a 32-bit RISC-V core. Designing a core is not a new thing. A big problem of the existing RISC-V cores is that while there is enough information on how to use a core in an application, it is very difficult to understand the low-level design and how the core works, because the design steps are not well documented. So we aim to make our design simple, and by truly documenting it, we aim to make it easy to understand for everyone. We have aimed to implement the I-base integer set, M standard extension, and machine-level ISA. I will explain what are those in the following slides. Okay, let's move on to our design process and start with the design of the integer pipeline. These integer instructions are the smallest set of instructions that make the core capable enough to execute most of the programs. For RISC-V, the specified instructions can be divided into 4 groups. Arithmetic instructions like addition, subtraction, logic instructions like exclusive or control transfer instructions like branch and jump, and finally memory instructions like load and store instructions. To design the circuitry that will carry out all of the integer instructions, we design a data path for each instruction separately using the functional units that we have. These functional units are registers, memories, adders, multiplexers, and etc. For example, for add instruction, we need an instruction memory that we will fetch the instruction from, a register file that we will read the data that we will do an addition on, and finally the arithmetic and logic unit here to do the adding operation. Like this, we construct all of the data paths for each instruction, and after that we combine all of instructions to achieve the complete data path that will be able to carry out all of the instructions. This data path is complete, but it has a very big drawback. All of the instructions are done in one clock cycle, and the slowest instruction, which is with the longest data path, determines the clock speed and therefore limits the performance. To overcome this, we use a method called pipelining. It's a very commonly used method. The data path is split into stages, and pipeline registers are inserted between each stage. At every clock cycle, data and control signals are transferred to the next stage by pipeline registers, and the instructions move along the pipeline. An instruction is finished after it reaches the final stage, and after the operations are done in the final stage, the instruction is done. The pipelining enables the core to work on higher frequencies, and therefore throughput is significantly increased. As we can see in the diagram, we have split the data path into 5 stages and therefore inserted 4 pipeline registers. Okay, with the integer set, the architecture that we will carry out integer instructions are done, we move on to the next stage, which is the design of the privilege architecture. In a typical computer, there are several levels of privilege in the hardware level for security purposes. Traditionally, each level is associated with a mode of operation, and at any given time, the software is running in one of the available modes. The important part is that each mode has a certain level of access to the underlying hardware. For example, the mode with the highest privilege level has access to all the registers and memory regions in the core, whereas the mode with the lowest privilege level might have access to only a limited portion of them. This privilege system is also important for a proper execution environment. In a typical computer, several programs run together at a given time. The implementation of this privilege level scheme enables the programs to work without being able to interfere with each other. There are 4 privilege levels described in the RISC-V specification sheet. With implementing these privilege levels, we are now able to control and monitor the status of the core. Each level has its own dedicated control and status registers. These registers, with the help of added instructions, allow the core to handle interrupts and exceptions. From these specified levels, the one with the most privilege, namely the machine level, is mandatory. The rest are optional to implement, and we also only implemented the machine level as well. The most important job of the privilege architecture is to handle interrupts and exceptions. This is done with an implemented state machine. The arithmetic state machine diagram can be seen here. When there is a pending interrupt, firstly, the pipeline is flushed, meaning that the instructions in the pipeline pipelines exit the pipeline. After that, the handler address specific to the pending interrupt or exception is calculated, and the program counter that points to the current instruction is set to the address to execute the code that handles the interrupt. A CSR unit containing the state machine and CSR registers was designed and then implemented to the core. The updated pipeline diagram with the privilege architecture can be seen here. We again see our pipeline stages, and above them, the CSR unit is placed. Okay, with the privilege architecture is also implemented, we move on to the next and our final step of design of the M extension. The M extension is an addition of set of multiplication and division instructions to the repertoire of the core. It includes 4 instructions for the multiplication and 4 instructions for the division for the 32-bit configuration of RISC-V. Those instructions are again specified in the RISC-V spec. The arithmetic circuits are realizations of algorithms constructed for carrying out the desired operation. So we needed algorithms that we will implement as multiplier and divider circuits. After a literature review, we constructed suitable algorithms for multiplier and the divider. We kept the required clock cycle, area, and complexity in consideration when we decided on the algorithms. We tried to not to lower the current speed of the processor before addition of the M extension. Now I will briefly describe our algorithms that we have used as a basis for the multiplier and divider circuits. For the multiplication, we used an algorithm that enables us to design a pipeline multiplier circuit to improve the speed. The operands A and B. Can you see my cursor?
Yes, we can see the.
Okay. The operands A and B, the multiplication operands, are partitioned into high and lower parts, namely A high and A low, AH and AL for A, and again same for B. After that, the multiplication of A and B can be written as this equation here. After that, we again partitioned each operand in each term again. For example, for A high H, we partitioned it to AH and AH low. We did that to every operand. And we now have achieved partial products that we will need to add in a proper way to achieve the final result. We can see the visualized version of this algorithm here. Partial products are the results of the multiplication of those smaller parts, and we need to add them and shift them for some amount and add them together to achieve the final result. With our multiplier algorithm ready, we constructed a circuit that realizes the algorithm. In the first stage, we obtain the partial products, and after in the second stage, we add them together in a proper way to achieve the final product. Now, for division, we constructed an algorithm that calculates the 2 bits of the coordinate in each clock cycle, and therefore needs a total of 16 clock cycles to calculate the 32-bit coordinate result. The remainder is also ready at the final clock cycle. The inner for block here represents the calculation of 2 bits of the coordinate in each clock cycle, and it is repeated 16 times in outer for block to achieve the final result. We see the visualization of the inner for block here. We needed 2 subsector arrays, and this block is the inner for block. With the division algorithm also ready, we again constructed a divider circuit to realize the algorithm. For the divider circuit, we have a divider block including 2 subsector arrays. There is also control unit that is responsible for correct inputs to the divider block and directing the outputs from it. In each clock cycle, again, the 2 bits of the coordinate are calculated and saved in a register. As we can see in the arithmetic state machine chart of the divider here, after a start signal is given to the circuit, after the result is calculated in the 16 rounds, and the final result is ready. Our designed and previously explained circuits are capable of executing on unsigned binary numbers, meaning that they cannot work correctly with the signed numbers, negative numbers. But there are instructions that have signed operands in the M extension. So we combine the multiplier and divider circuits on a top module that we have called muldiv with input and output handling circuits to enable them to work on signed operands if necessary. The input handling circuit here converts negative numbers to positive if necessary by checking the signs and current instruction. And after the calculations are done in the either divider or multiplier block, the result is converted back to negative again if necessary, and the final result is ready. With control unit and control components, the circuit muldiv is capable of executing all of the M standard extension instructions. We integrated the muldiv to the rest of the core, specifically to the execute stage near to the LU, and this with addition of the muldiv to the core, we now have the finalized version of the pipeline. We now have a 32-bit core capable of working with basic integer and M extension instructions, and also we have with the privilege architecture, meaning that it can handle exceptions and interrupts. The RV32IM means stands for 32-bit I and M integer M extension instruction extensions. As we have aimed to our work to be open and accessible to others that are interested, we documented our design steps carefully and uploaded our work on GitHub. And we have now a decent core for academic purposes. There is also room for future work. The core can still be optimized to be faster, and other specified extensions can be added to it. The core is ASIC synthesizable, so chip tape-outs can also be done. The core can also be used in academic projects because of its relatively easy to understand design. With that, I have finished my presentation. Thank you for listening.
Okay, thank you very much. It's a 15 minutes exact presentation. It's also thank you for you keeping your time. And so you forget to give the GitHub addresses probably. And if there is a short question,
okay,
I will only allow a short question if you have. Are there any questions?
Can you hear me?
Yes, Latif, you have, please, a short question. You have already consumed our times. Okay.
Yeah, it's very short. I just want to ask Yasin if they have made any comparison from the existed course.
We aim our core to be simple, so we from the start didn't aim to be the core to be a fastest or smallest core. We just aim to be it to simple and easy to understand, and also we aim to truly document our design steps. So we didn't compare it with other cores like specifically for speed or area, but we have compared with them in terms of easiness of understanding and good documentation.
Thank you so much.
So it's also in the GitHub. If someone wants to compare, it is already possible.
Yes.
Okay, thank you again, Yasin. That's a good
You're
work.
welcome. Thank you, Erhan.
Let's start the next presentation. I guess Nazim Altar is here.
Yes.
Okay, Altar, please start. And 15 minutes, please try to best to keep in time.
Okay, can you see my screen?
Yes, we can see your slides.
Okay, hello everyone. I'll present our paper named Multi-Layer Perceptron Hardware Accelerator on RISC-V Processor. And let's start. And the need for domain-specific hardware architectures of neural network models is increasing with the rapid development of robotics, autonomous cars, and IoT devices. For these data-driven systems, new fast and efficient hardware methodologies are introduced recently. In this study, a comparison with the general purpose RISC-V processor and the customized version of it for deep feed-forward neural networks is presented. The customized version consists of local memory structure and special flat computing unit, and an interface to communicate with core. We aim to show by using the strong size of both these two hardware and the co-design software, more efficient and fast architectures can be achieved. multi-layer perceptron networks, also known as deep feed-forward networks, consist of perceptron structure. Perceptron has introduced in the late 1950s by Rosenblatt. It mainly performs a weight sum of its inputs, and after that goes through a nonlinear activation function. And this structure actually acts like a linear classifier. MLP networks has many layers, which has many perceptrons in it. In this way, more complicated classification problems can be solved. The network has two stages. First is forward propagation, where network decides what the output class is. And the second is back propagation, where network learns from its wrong and right decisions. At the beginning of the project, Fashion Amnesty benchmark problem is chosen to validate the network performance. The data set consists of 28 times 28 pixel size black and white cloud photos, 10 different classes, and each one has 7,000 instances, which ends up 70,000 total number of instances. We choose Fashion Amnesty classification problem for performance evaluation, since it is a more complicated data set than the classic Amnesty handwritten digit problem, where modern MLP structures can achieve up to 99% accuracy. So that more feasible results can be obtained with this Fashion Amnesty dataset. It can be seen that even complicated MLP structures can only achieve up to 87% accuracy on this specific benchmark problem. We first implement the network structure on Python to achieve optimum parameter values by observing the results. We only use basic numerical libraries on model and evaluate results with the aid of well-known metrics like confusion matrix. By taking the hardware resource into account, we implement 3-layer MLP. First 2 layer has 16 perceptron each, and output layer has 10 perceptron, which corresponds to 10 class of the Fashion Amnesty problem. We implemented dropout, momentum effect, and adaptive learning methods to increase accuracy of the system. The ReLU function is used as nonlinear function to decrease the hardware complexity. It can be seen that our tiny network has achieved up to 84.5 accuracy with these improvements on the software. After obtaining weight matrix values on the Python training phase, we implemented the inference layer without backpropagation on C language to be used on RISC-V processor. The C model is validated by comparing GCC compile results with the Python model results. RISC-V GNU toolchain is used to map this model into RISC-V processor environments by generating the RISC-V assembly codes. RISC-V environment is selected to work on it since it has a great flexibility to modify it, as Yasin mentioned earlier presentation. 4-stage in order 32 with RISC-V core is used in this project. It also supports FPGA core via auxiliary processing unit bus, APU bus interface. Palpino environment is selected since it has UART and SPI interface that are used throughout our project. It also supports modern AXI4 interconnect. The other reason to select this controller is the availability of both RTL simulation and FPGA implementation version of it. By the way, it is implemented by ATH Zurich. One of the main goals of this project was working on RISC-V environment and customizing it according to the MLP application. After the setup of Palpino, UART function is implemented to provide an alternative debug method through our computer. Also, SPI bootloader structure is implemented by using external flash memory to load bigger size codes easily. In this method, the bootloader code is kept in both boot ROM and the instructions are loaded into the instruction RAM. Otherwise, it is necessary to load the code into boot ROM, which has less array than RAM. Once the MLP model was written in C, it is observed that network parameters need more space than Palpino data RAM has. Therefore, the memory structure was modified to be able to load all parameters. In both HDR level and compiler level linker scripts were modified in the project for this purpose. After the model was loaded and the result was validated with integer instructions, single float instructions were activated to run the model in a faster way. The method also known as hard float is used for this. Palpino has a float point unit, which is connected to the core via IP bus, as mentioned earlier. To utilize this unit, the original systems, also system level scripts, are used by changing the required parameters. And after done the modifications on Palpino, we mainly motivated to accelerate the high density data-driven neural network structures by using highly parallel float point computing unit and the local memory structures. With the real-life constraints on transfer sizing and working frequency, computer architects have been working on domain-specific architectures recent years. Dark silicon concept is introduced with the idea of allocating the different parts of the chips to different jobs by running them in parallel. In this study, we aim to implement this idea with a parallel processing unit near the core. Also, recent years, it is shown that main time and energy consuming element of these data-driven systems is the read-write operations, accessing the RAM mainly. So we aim to overcome this problem with local memory structure, which keeps the weights parameters of the network near the processing unit. In the multi-layer perceptron network, the most used function is multiple accumulation operation. It simply multiplies the input and weights. After that, adds the result to previous output. It is a basic multiplication process. Once the MAC output is obtained, the output passes through the activation unit, which applies a nonlinear function to its input. In the design, this structure is taken as the basis, and multiplier and the other hardwares were designed considering 32-bit IEEE float number format. And ReLU is chosen as a nonlinear activation function for the sake of hardware design simplicity. With these two designs, simple neuron structure is obtained. And after that, this design is reproduced multiple times according to the model parameters. So by doing this, highly configurable and parallel design unit has obtained. The overall design view can be seen here. Once the computing unit design is completed, memory structure is built to carry the data to computing unit as efficiently as possible. For this purpose, a scratchpad design, which is used commonly in embedded system hardware, is added to the architecture with simple RAM blocks. Scratchpad is a local memory structure to provide a space for special and commonly used variables. It differs from cache with its simplicity. And the weight coefficients of each layer are kept in these three memory structures. Thus, overall efficiency of the system is increased since the same weights are used for different inputs after the training phase. We also designed an AXI4 full handler to provide efficient communication between a custom designed unit and the RISC-V core. And also an internal state machine design has implemented, which is triggered by the core via AXI bus to perform inference layer on this specific hardware. It's also can be seen a UART module is implemented to communicate between the computer and the FPGA, and also SPI function is used to communicate between core and the flash ROM of the FPGA. So the study is focused on three main comparisons. First one is to run a big float model like MLP algorithm on only integer and multiplication instruction sets, known as soft float. Secondly, to run the same model on both integer multiplication and float instructions. Finally, to run the same model on custom float hardware, and to observe the timing and behavioral differences between these three hardware results. In table 1, the comparison between these three methods can be found. In the table, also compiler level optimization comparisons are given. And it is obvious that software level optimization is as important as hardware level optimizations. And as a result, in the study, a neural network accelerator was designed and comparison between general purpose computers and this custom hardware was conducted. A complex float point model was first implemented in software and optimized to obtain most accurate coefficients. After that, C-level implementation of the model was written and run on the general purpose RISC-V processor. This step is divided into two. Firstly, it was tested on only IM instructions. Secondly, it was tested on IMF instructions. Finally, the custom hardware design was completed and added to the architecture. Same model was run on the hardware with the same inputs, and results were very clear to us. With custom hardware, the speed can be improved up to 10 times for end-to-end process. Thus, the hardware co-design with both general purpose hardware and the custom hardware are presented to show significant improvements can be achieved by using strong size of both hardware. So thank you for listening for me.
Thank you, Altar. It was a very nice presentation. And we have some small times for the question. Are there any questions? Maybe I can ask one question. So you generated this network using this Python environment. Am I correct?
Right.
And then all the weight was how long? I mean, it generated 64-bit weight parameter?
32-bit float parameters.
32.
And yeah, we actually training time was about 5 minutes.
5 minutes.
5
Okay.
minutes on Google Colab GPUs, by the way.
Okay. Do you know that are there any tool that at the end you design a network consists of, let's say, 32-bit or 16-bit floating arithmetics, multiplication or adder? So is it possible to, or are there any tool to, for the learning session to use that kind of, let's say, operations embed to learning process? So you use Python or something, but I wish to modify in the Python during the learning all the multiplications and adding operation is designed by my purposes. So let's say 16-bit floating or 16-bit integer numbers. Use this kind of operations during the learning. And then when you map that one to architectures in your hardware, then there will be correct operations also in the hardware. Do you know any tool during in the Python or others use customized operations for the multiplication or also adding?
No, I unfortunately I didn't see an implementation like that.
Okay. Then when did you compare the performance of your network after on the hardware and comparing with the result in the obtaining the Python?
We firstly implemented in the float using float point unit of the RISC-V, and after that we implemented it on our custom hardware, and we just compare it by speed.
Okay. Not what do you call
Not
it?
energy or area.
You just energy. Okay, thank you. Okay, thank you. It was a very good presentation. Also, thank you for the answering the question. And so we have the last talk, and probably Elif, I think, she's going to present.
I'm sharing my screen.
Okay, please. And then you can start after you share the presentation. Okay, I can see. You can start.
Hello, I am Elif from Istanbul Technical University. Me and my teammate Ilayda recently completed our graduation project that I will be presenting you today. In this presentation, I will introduce you the project, an FPGA implementation of Gibbs rotation-based digital architecture for computing eigenvalues of asymmetric matrices. We presented our Gram-Schmidt-based eigenvalue calculation study at several non-scale networks and applications conference held in September. And today, in this study, I will present the Gibbs rotation-based study and compare the two algorithms in the conclusion part. These are the main topics that I will mention during the presentation. Eigenvalue calculation is essential in communication technologies and digital signal processing fields. The calculations are handled with iterative method causing too much time consumption. This study proposed a time-efficient parallel architecture based on triangular Ozturk array for computing eigenvalues of asymmetric matrices with real values. The QR algorithm is used to compute the eigenvalues. In this study, QR algorithm based on Gibbs rotation algorithm is implemented on FPGA and compared to the MATLAB results. There exist two popular algorithms for eigenvalue calculation, Jacobi theorem and QR algorithm. Since Jacobi theorem is insufficient for asymmetrical matrices, we choose to work on QR algorithm. QR algorithm calculates eigenvalue through the factorization of Q orthogonal and R upper triangular matrices. This is done by QR decomposition block. Then these Q and R matrices are given to the matrix multiplication block. The RQ multiplication forms the input of the QR decomposition block at the next iteration. This iteration continues until the lower triangular elements of the input matrix approach 0. This is provided via check diagonality block in the diagram. Once yes is answered by the block, eigenvalues are obtained from the diagonal elements. However, if the matrix is asymmetrical form, complex conjugate eigenvalue pairs may exist. In such a case, the QR algorithm becomes insufficient to calculate these complex pairs. The control of such pairs is done via check complex conjugate pair block in the diagram. If yes is answered, the complex conjugate pairs are calculated in the quadratic equation solver block. Within the scope of the undergraduate thesis, QR decomposition block using both Gibbs rotation and modified Gram-Schmidt were designed and compared. Here, Gibbs rotation algorithm is used for QR decomposition block. Gibbs rotation algorithm search for lower diagonal elements to convert 0. Each element is converted one by one, starting from the first column, second row. At 9, 5, and 6, sine and cosine values are calculated. We will analyze this step further in digital design of the Gibbs generation blocks. This G matrix gets the sine and cosine values according to elements that will be converted to 0. As can be seen in the line 11 and 12, R and Q values are updated via G matrix. This step will be explained further in digital design as row update block. After line 12, the process is iterated until an upper triangular matrix is achieved. Column-wise Gibbs rotation is implemented based on TCA architecture. The architecture consists of Gibbs generation and row update blocks as can be seen on the figure. The GG block sends the sine and cosine values to the row update block. The same signals are sent to all RU blocks in the same row. In addition, since all columns of the input matrix are processed in the RU blocks at the same time, parallelization is achieved. Thus, a time-efficient system can be designed. As mentioned before, CV Gram-Schmidt Gibbs rotation converts lower diagonal element to 0 so as to obtain an upper triangular matrix. In the first step, the lower diagonal elements of the first columns are converted. The updated first row will be from the first row of the final matrix. Then the updated matrix is given to the step 2. In this step, the 3 by 3 matrix part shown in the figure is extracted to convert the elements of the second column to 0. Similarly, the second row will be from the row 2 of the final matrix. As a result, the upper triangular R matrix is achieved at step 4. The figure depicts the first Yavuz generation block. In the GG1 block, sine and cosine values and T and L parameters are calculated via fundamental arithmetic models and square root model. Then these parameters sent to RU blocks. As can be seen, these values are calculated for each column rather than each of diagonal elements. By this way, TCA architecture is implemented and thus parallelization is provided. It should be noted that this figure shows only the GG1 block. This is due to decreasing size of the entering matrix. As the signs decrease, less modules are required for parametric calculation. For a more optimal system, the inner modules are extracted and GG modules are minimized. Again, this RU block depicts only the RU blocks for the first row. Similarly, as the row number decreases, less inner modules are needed. Thus, the RU blocks get smaller. When examining RU1, the signals coming from GG1 module enters the multiplication blocks for the calculating the row elements and updated matrix elements. GG and RU blocks can calculate only the upper triangular matrix R. Column-wise Gibbs rotation becomes insufficient in calculating the orthogonal Q matrix due to using the same values in each column for parallelization. For this reason, an addition Q estimate block is needed. This block performs the equation A equals QR to find the Q matrix. In the process, each element of the same column are calculated at once, while each row element is calculated sequentially. As a result, another static array architecture is formed. Hence, time efficiency is strengthened via parallelization. QRD block is followed by matrix multiplication block. In this block, the entering Q and R matrix performs the RQ operation. This calculation is handled by a 16 parallel inner matrix multiplication block performing the following equation. Resultant each element equals to each row of R multiplied by the jth column of Q. The parallelization of this equation provides time efficiency in digital design. However, array utilization is compromised in this process. In diagonal check block, the lower diagonal elements shown in the black circles are compared to 0. If equality is provided for all these elements, the real eigenvalues are obtained from the diagonal elements. If not, iterations are continued. It should be noted that lower diagonal elements placed one row below the diagonal ones are not checked. This is due to the possibility of complex conjugate pair existence. If these pairs are non-zero, it implies that there is complex conjugate pairs corresponding to these plates. In the example, lower diagonal elements except from x3 to are all zeros. This implies that complex conjugate eigenvalue pair exists. In complex conjugate pair check block, a 2 by 2 matrix part is extracted having non-zero elements as is 2, 1 elements. To find the value pair, the determinant of the 2 by 2 matrix is calculated and equalized to 0. The obtained 2 by 2 matrix is given to the quadratic equation solver block. The schematic image is taken from Vivado is given here. The signals formed by the matrices are highlighted. A simulation image is given on the dispatch. On the left side of the simulation screen, the columns of the input and Q matrices and the elements of the R matrices are given. The exit flag signal produced by the check diagonality block became active after 3 iterations and stopped iterations. The signal given in the orange box is the final update matrix updated through the iterations. Since it's all one below lower diagonal elements, not 0, it is lost in the last iteration. It's understood that it contains complex results. And extracted matrix is given to the quadratic equation solver block. At the end of this matrix, the complex conjugate pair is obtained, which is indicated in the green box. In this simulation, a 4 by 4 input matrix is used. Each element consists of 16 bits in the form of 1 slide, 5 decimal, and 10 fraction bits. In the simulation, using 100 microhertz frequency, the results were completed in 25 microseconds. The simulation image here is taken from our previous work. Starting from this slide, the results of the two algorithms will be compared. In the Graph-Schema simulation, we see that the results come in 33 microseconds with 4 iterations. This table shows the operation usage according to matrix size n. While examined, array usage is a favor of Gibbs notation digital design when n is small. However, as n increases, the advantages become on the modified Graph-Schema algorithm. In this table, eigenvalue results error are compared. Although error rates are small for both algorithms, Gibbs rotation outputs are closer to MATLAB results. Still, all results have an error rate less than 2%. At the end of the study, a complete digital architecture of eigenvalue calculation is implemented by combining and customizing the reference work. While designing QRD blocks, TCA architecture is taken as a base to achieve time efficiency by parallelization. However, since optimization is not set an interest of this work, IP cores are used. The operation speed can be increased further by optimizing the IP cores, block delays, and frequency. Based on the example given in this study, Gibbs rotation reaches the results faster and with more accurate values. Graham-Schmidt algorithm, on the other hand, has an easier architecture to implement in TCA architecture. Thank you for your attention. We will please answer your questions.
Okay, thank you, Elif. At the end, we are on the time, I guess. Are there any questions? Maybe I have some question. So as you see in the previous presentation, people likes to use RISC-V. So it's very popular nowadays. So what do you think? Your design fully digital, and seems to be it's hard to implement everything in the fully digital. So is it possible to make it some process take to in the process of something like RISC-V? What do you think about it?
Maybe it can be used, but I think it will be very difficult because the system is very big size, have a big size, and have a lot of latency. Actually, I don't know, but I think it's not suitable for RISC-V at this level. Maybe it can be optimized and then it can be used in the RISC-V.
But my question is, in fact, I just want to direct you, which part of these algorithms can be carried to the software? So, so I imagine that there might be some eigenvalue accelerator for the RISC-V process.
Okay.
Which part of the algorithm can be implemented in the hardware, and which part should go to the software part?
Okay, maybe the square root and divider modules in the software part, because these parts in the most difficult and most usage parts. And that's all. Square root and divider, maybe.
Also, do you think that precision, so bit word size, it's worth to increase the word size or to increase the word size of the multiplications and also this square root computation will improve to the precise result for the obtaining the eigenvalue?
I think yes, because we use 10 bit for fraction bit parts, and if we increase these bits, and our results will be more accurate and more better, I think, because our system 10 bit fraction is mean that 10 to the power -3, and we found -2 error percentages, and because maybe if we increase the size of fraction part, the results will be better, I think.
Also, if you are now in the industry, so do you think that we really need to compute the eigenvalue with a high precision? No, you don't have any idea?
I think yes, because for example, eigenvalues are using in direction of arrival or some algorithms in digital signal processing, and these algorithms we need to these algorithms at a very çok kısa zamanlarda ihtiyaç duyuyoruz.
For you, you mean for the computation time?
Yeah, for the computation.
But is it the error tolerance? What might be? I mean, is it really needed to compute it with a high precision?
Actually, I don't know. Maybe it's not, because in the real systems, the noise variables, like if we be at the noise, that be similar to our error percentage.
Okay. Thank you very much. I think any other question? And if not, I would like to thank all the attendees and also all the presenters to attend the conference and to give their talk. Also, I would like to thank to ELECO organizers and also all the technical workers. They make available for us this environment, and we can discuss and we can share our results. And I very much like to attend the ELECO conference. It's a good opportunity for us in Turkey to have something like this one. And thanks to ELECO organizers, also all the hard workers for the ELECO, and thanks to all the attendees. This is end of the session. I wish you healthy days. Okay. So I'm going to finish this session.
Thank you so much.
Thank you. Have a great day.
Thank you.
Thank you.